23.1 Electric field of a continuous charge distribution. We will now outline the key topics covered in our study of electric fields. We will begin by exploring the concept of continuous charge distributions, establishing how we transition our mathematical formulation from simple discrete summations to vector integration. To make these calculations possible, we will define three key metrics, which are volume, surface, and linear charge densities. We will then lay out a step-by-step problem-solving strategy. Finally, we will apply this strategy to calculate the electric fields for three specific geometries, which include a uniformly charged rod, a ring, and a solid disk. In many real-world scenarios, electric charge is not a collection of discrete points, but is instead distributed continuously along a line, over a surface, or throughout an entire volume. To find the total electric field created by such an object, we conceptualize dividing the entire charge distribution into tiny, microscopic elements, each containing a small amount of charge called delta Q. We then apply the superposition principle by summing the individual field contributions of all these small elements. As shown in the equations, the field contribution from one small element is the Coulomb constant multiplied by delta Q divided by the distance squared and directed along the unit vector. The total electric field at a given point is approximately the vector sum of all these individual pieces. Taking this concept to its mathematical conclusion, we consider the limit where the size of each small charge element approaches zero. In this limit, the discrete summation transforms into a continuous vector integral over the entire charge distribution. The electric field is formally expressed as the Coulomb constant multiplied by the integral of the differential charge element, dAq, divided by the distance squared, and pointing in the unit vector direction. To evaluate this integral in practice, the charge element dAq must be rewritten in terms of A charge density and geometric variables. Because this integration is a vector operation, the field components must be resolved and integrated appropriately. To perform these spatial integrals, we must define three types of charge densities based on how the charge is spread out. For a total charge uniformly distributed throughout a three-dimensional volume, we use the volume charge density, denoted by the Greek letter rho, defined as total charge divided by volume, with units of coulombs per cubic meter. For a charge spread over a two-dimensional surface area, we use the surface charge density, sigma, defined as charge divided by area, with units of coulombs per square meter. Finally, for a charge distributed along a one-dimensional line, we use the linear charge density, lambda, which is charge divided by length, measured in coulombs per meter. When dealing with continuous charge distributions, particularly non-uniform ones, or when setting up the limits for our integrals, we express the infinitesimal charge elements using these density definitions. We can substitute the charge element, dEq, in our electric field integral with spatial coordinates. Depending on the physical geometry of the problem, dq is equal to the volume charge density times the differential volume d, v, the surface charge density times the differential area dA, or the linear charge density times the differential length dl. Making this substitution is a critical foundational step before performing the actual integration. Here is a reliable problem-solving strategy for evaluating electric fields. First, conceptualize the problem. Imagine the physical shape of the object, and use symmetry to visualize the direction of the net electric field. Second, categorize the situation to determine if you have discrete point charges or a continuous charge distribution. Third, analyze the problem by replacing vector sums with vector integrals. Express the charge element dAq in terms of appropriate spatial coordinates, and heavily utilize symmetry to identify field components that cancel each other out, saving you from unnecessary math. Finally, finalize your result by checking its behavior at extreme limits. For example, If you measure the field from a very large distance, the mathematical result should resemble the simple electric field of a point charge. Let us look at our first practical example, which is finding the electric field of a uniformly charged rod. We have a rod of length L with a uniform linear charge density and a total positive charge Q. We want to determine the electric field at point P, which is located on the axis of the rod, a distance a from its left end. By conceptualizing the problem, we know that since the entire rod is positively charged, every small segment of the rod will produce an electric field vector at point P that points to the left, directly away from the continuous charge. To analyze this geometry, we select a small arbitrary segment of the rod with length dx. The charge of this segment, dq, is equal to the linear charge density lambda times dx. The magnitude of the differential electric field from this one segment is the Coulomb constant times lambda dx, divided by the distance x squared. To find the total field, we integrate this expression from the left end of the rod, where x equals a, to the right end, where x equals L plus a. Evaluating this integral shows that the total electric field equals the Coulomb constant times the total charge Q, divided by the product of a and the quantity L plus a. If we check the limit where the distance a is much greater than the rod length, the denominator simplifies, and the field perfectly approximates that of a single point charge. In our second example, we will calculate the electric field generated by a uniform ring of positive charge. The ring has a radius a and carries a uniformly distributed total charge, Q. We are looking for the electric field at point P, located a distance x from the center along the central perpendicular axis. Symmetry is our best tool here. If we pair up any two charge segments on completely opposite sides of the ring, their electric field components that are perpendicular to the axis point in opposite directions and completely cancel out. Therefore, we safely ignore the perpendicular components and only need to integrate the field components that are parallel to the x-axis. The parallel component of the electric field from one segment is the Coulomb constant times the charge element dq divided by the distance r squared, multiplied by the cosine of the angle theta. Using the right triangle geometry shown on the slide, the distance r is the square root of a squared plus x squared, and the cosine of theta is x divided by r. Substituting these geometric relations into our integral reveals that x and a are constant for all charge elements around the ring. We can pull them out of the integral, leaving only the integral of dq, which simply becomes the total charge, Q. The final result is the Coulomb constant times x times q, all divided by the quantity a squared plus x squared raised to the 3/2 power. Our final geometry expands the empty ring into a uniformly charged solid disk of radius r with a surface charge density sigma. We want to find the electric field at a point P along its central perpendicular axis. To solve this continuous surface problem, we can mathematically model the solid disk as a nested set of concentric thin rings. A single representative ring within the disk has a radius r and an infinitesimally small width dr. The amount of charge on this thin ring, dq, is simply the surface charge density multiplied by its area, which is 2 pi r times the width dr. We can take the electric field formula we derived for a single ring and substitute our new expression for dq to find the field contribution from just one thin ring element. To find the total field of the disk, we integrate this expression over all the rings, starting from a radius of 0 at the center out to the maximum radius, r. Evaluating this integral gives us the exact electric field for a finite charged disk. An interesting property emerges if we take the limit where the disk radius r grows toward infinity. The formula reduces to the surface charge density divided by 2 times the permittivity of free space. This proves that an infinite plane of charge produces a completely uniform electric field that does not weaken with distance. To summarize our key findings, the electric field of any continuous charge distribution is calculated by integrating the individual field contributions from infinitesimal charge elements. Using volume, surface, or linear charge densities is an absolute necessity for converting the theoretical charge element dq into practical geometric differentials like dx or dr. You should always look for physical symmetry, as it significantly simplifies calculations by canceling out certain opposing field components. Finally, remember that at extremely large observation distances, finite continuous charge distributions mathematically behave just like localized point charges, while an infinite plane of charge produces a perfectly uniform electric field everywhere in space. Before we conclude this topic, please consider these review questions to test your conceptual understanding. First, think carefully about why the calculated electric field of a uniformly charged ring drops completely to zero exactly at the center of the ring, and how this phenomenon directly relates to the concept of vector symmetry. Second, under what specific mathematical condition does the exact expression for the electric field of a charged rod reduce to the simple point charge formula, and what is the physical interpretation of taking that specific limit? Reviewing these specific scenarios will greatly strengthen your problem-solving intuition